Now we are going to see MOSFET. MOSFET means it's metal oxide semiconductor field effective transistor. Okay, this is the symbol of the MOSFET. This is N channel MOSFET. This one is P channel MOSFET. Okay, MOSFET are the majority carrier devices. N channel means the majority carriers are electrons. P channel means the majority carriers are holes. I mean positive charge. Okay, MOSFET has three terminals, that is gate, source, drain. Okay, then P-channel MOSFET is used to switch the positive supply. Okay, and N-channel, this one, P-channel MOSFET is used to switch the positive supply, and N-channel MOSFET is used to switch the negative supply. Okay, once the gate source drive is applied, okay, current flows from drain to source. Okay, when we remove the gate source drive, current will stop. Actually, the gate has full control over the MOSFET. Whenever if we don't want to, if we don't want the current, then we can just by removing the gate source, what is that? Gate source signal, we can switch off the MOSFET. Sorry, gate source drive, we can switch off the MOSFET. Okay. So like the turn on turn off times are very small for MOSFET, so they can be operated in high frequency circuits. Okay, MOSFET has a positive temperature coefficient. Positive temperature coefficient means that what will happen? The current will flow. If the current rises, so resistance also will rise. Okay, because of that the junction temperature also will rise. So if it has positive temperature coefficient, then the current path will select the different path where the other instruments are connected. No, different path or parallel path. Current select the parallel path. So, if MOSFET has positive temperature coefficient, so the paralleling is very easy. Then this is the structure of the MOSFET. Just by seeing the figure, you just explain as it is. This is P-type body region. These are the N plus regions. N plus regions are heavily doped. That is, doping level is 10 to the power 19 per centimeter cube. P-type body region is moderately doped, that is 10 to the power 16 per centimeter cube. Here, N regions are connected with the source and drain. Okay, gate is also there, but gate is not directly connected to the P-type body region. Between gate and P-type body region, metal is there. The next layer, this is metal oxide. I mean silicon dioxide. Okay, is present. This serves as an insulating layer. Okay, then when we apply, when we made the gate source voltage positive, I mean we are applying positive voltage to the gate. Okay, gate is positive with respect to source. If we apply, then accumulation layer of electrons will be formed, and this will come to the drift region. Already we know in the drift region some holes are also there. So electron and hole forms a pair. Okay, then free electrons will be there. These free electrons will get more kinetic energy, and it will knock off other atoms to release more electrons. Okay, whenever if we want to switch off the MOSFET, if we remove this VGS, I mean gate source voltage, if we remove this, then immediately the accumulation layer will be vanished. Okay, the MOSFET will be switched off. Switched off. Okay, so um, the induced breakdown voltage, no, That depends upon the uh, thickness of the drift region. This is the drift region. So, induced breakdown voltage depends on the thickness of the drift region. These are the VI characteristics of the MOSFET, that is steady state characteristics. The graph is plotted between ID and VDS. ID means drain current, VDS means drain source voltage for various gate source voltages. Okay, here the gate source voltage is kept as VGS1. Then above that VGS2, VGS3, like that it will increase. Okay, this region is known as ohmic region. Okay, the curve is no, this region is known as ohmic region, and this one is cutoff region below VGS1. This is cutoff region, and the center part of the uh, curves, no, that is known as active region. Actually, MOSFET works in ohmic region and cutoff region. In active region, MOSFET works as an amplifier, so that is mainly used for the amplification properties. In the ohmic region, MOSFET is turned on. In the cutoff region, MOSFET is turned off. Okay. Then VGS, that is gate source voltage. If the in cutoff region, gate source voltage is less than gate source threshold voltage, VGS/TH. Gate source threshold voltage means a minimum voltage that is required to activate the active components. Okay, active components means the components in the circuit which are rely on external power. That is the threshold voltage. So in cutoff region, VGS is lesser than VGS TH threshold voltage. Okay. Then we'll see the merits of the MOSFET. MOSFETs are majority carrier devices. P channel means positive carrier devices. N channel means electron carrier devices. They have positive temperature coefficient, so paralleling is easy. Positive temperature coefficient means that if the current increases, the resistance of that place is also that junction also increases. So current will select the different path, that is parallel path, which is in the circuit. Okay, that's why we have written paralleling is easy. They have simple drive circuits. They have short turn on turn off times, so they can be operated at high frequencies. They do not require commutating circuits. Commutating circuits means the circuits which are used to turn off the devices, but MOSFET does not require any commutating circuits. By simply by removing the gate source drive, we can switch off the MOSFET. Then demerits, that on-state losses are very high in MOSFET. They are used for low power applications. They are suffering from static charge. Static charge means unwanted sound we will get. That unwanted sound is created due to the presence of electric charge in the atmosphere. Sometimes between the metal or on the surface of the metal, the electric static charge will be there in the atmosphere. So that will create sound. Okay. Then MOSFETs operated in ohmic region and cutoff region. If drain source voltage is increased above BVDSS, that means uh, drain source breakdown drain source voltage, BVDSS. If the drain source voltage, I mean VDS, is increased above BVDSS, the MOSFET will be damaged. Breakdown drain source voltage. Next one, transfer characteristics of the MOSFET. The graph is plotted between ID and VGS, that is drain current and gate source voltage. Okay, we will get the graph like this. VGST means minimum positive voltage required to induce channel. This voltage will be a minimum positive voltage required to induce channel. This voltage will be 2 to 3 volts. Then merits already we have seen. Okay, demerits and applications we have seen. Again, for your reference, just I have given the note. Static charge means unwanted sound due to the presence of static electricity in the air. Next, we'll see the IGBT. IGBT is nothing but insulated gate bipolar transistor. It is the IGBT is the combination of BJT and Mosfet. Okay, see the symbol. This is gate, this is collector, this is emitter. Okay, so from this symbol itself, we can come to know that IGBT is the combination of MOSFET and BJT, because um, collector emitter circuit is from BJT and gate is from MOSFET. Okay, so it has three terminals. Then when a gate emitter drive is applied, current starts flowing from collector to emitter. By removing the gate emitter drive, we can turn off the IGBT. IGBT only this much is enough. Just I have given the figure. By seeing the figure, you try to explain. That's why I didn't write the notes here. Okay, this is the cross-sectional figure of the IGBT. There are P plus region, N plus region, N minus region, P region, N plus region, N plus region. Then gate, emitter, gate, collector is connected here. Okay, this is N minus drift region. There is a, if the gate emitter voltage is applied, gate emitter drive is applied, I mean positive voltage, and then current flows from a collector to emitter. Current flows from collector to emitter. Okay, this here when we apply the gate source voltage, what will happen? The gate source voltage accumulation layer of electrons will be created here. Accumulation layer of positive charges will be created here. Both are they will be introduced into the drift region. These electrons are also introduced into the drift region. The electron and positive and negative charges form holes. Form pair. So this will then remaining electrons. No, they are free. They are getting more kinetic energy. So they will knock off other atoms to release more electrons. Like that, it's working. Next, we'll see the silicon control rectifier, SCR. Okay, this is the structure of the silicon control rectifier. Again, there are P plus P, N minus P regions are there. P plus is heavily doped, that is 10 to the power 19 per centimeter cube. P region is moderately doped, 10 to the power 17 per centimeter cube. N minus region again 10 to the power 14 per centimeter cube. P region 10 to the power 17 per centimeter cube. Here, gate cathode is there. Okay. Anode is connected here. There are three junctions, J1, J2, J3. Just here, I have shown you the simplified structure of the SCR, that is anode, gate, cathode. There are three junctions. They are J1, J2, J3. Okay. When the gate cathode, when gate cathode junction, that is J3. Yeah, gate and cathode junction J3 is is forward biased. SCR turns on. Some carriers flow across J2. Okay, so what will happen? Internal regeneration starts and SCR turns on. So that means once if the SCR turns on, then the gate has no control over the SCR. So to turn off the SCR, we need to use commutating circuits. Okay, that we will study in the later chapters. Merits of the SCR: very small amount of gate drive is required since SCR is a regenerative device. So very small gate drive source is required. So as a gate drive is required. SCRs with high voltage and current ratings are also available. On-state losses are very less. Demerits of SCR: gate has no control once the SCR is turned on. Then we need external circuits, that is commutating circuits, to turn off the SCRs. Operating frequencies are very low. Snubber circuits, I mean RC circuits, are required for dV by dt protection. Okay. Snubber circuits means are required for dV by dt protection. dV by dt means rate of change of voltage with respect to time. If it changes rapidly, then that also helps to turn on the SCR. Okay, applications of SCR, they are suitable for the controlled rectifier. They are used in AC regulator, lighting and heating applications. They are used in DC motor drives, large power supplies and electronic circuit breakers. Okay, now this is the SCR characteristics and its mode of operation. This is the graph. This is the figure what we got. Okay, for various reading, the graph is plotted between IAK, anode cathode current, and VAK, anode cathode voltage. Okay, this quarter, first quarter, is known as forward conduction, forward blocking mode. Okay, in the first quarter, both forward conduction and forward blocking mode is there. This is on state. Okay, here the graph we will get, no, that will be like this. The graph what we are getting is like this. So this point is known as breakover voltage. This point is known as breakover voltage. So once the voltage comes to this point, the SCM will be turned on. Okay, these are the IG3, that is gate current. IG3 is greater than IG2, IG2 is greater than IG1. So if the gate current is greater, then SCR will be turned on immediately. Okay, VBO means that is forward breakover voltage. When VBR is reverse breakdown voltage. Sorry, VBO means forward breakover voltage, and VBR reverse breakdown voltage. Okay, IG1, IG2, IG3 are gate currents. Then now we will see the reverse blocking mode. For example, the connections are made as shown in the figure. This is PN junctions are there. This is anode, cathode, gate. Okay, gate, anode, gate, cathode. Okay, anode is connected to the negative supply of the voltage source. Okay, in reverse blocking mode, just we imagine these are the junctions J1, J2, J3. J1 and J3 are reverse biased, so J2 is forward biased. Okay, so in this mode, ACR does not conduct. A very small current flows from cathode to anode. Very small current flows from cathode to anode. Okay, this current is known as reverse leakage current. Okay, this mode is known as reverse blocking mode. In if VBR, reverse breakdown voltage, Once it reaches the voltage reaches the reverse breakdown voltage point, the reverse current increases rapidly. So what will happen? Because of that, heavy current flows through it. Due to this, large power dissipation takes place and SCR will be damaged. Okay, hence reverse voltage should not exceed reverse breakover voltage. Then next one is forward blocking mode. In forward blocking mode, the connections are made as shown in the figure. Okay, here this time in forward blocking mode, anode is connected to the positive supply of the voltage source. Okay, there are junctions, three junctions, J1, J2, and J3. In forward blocking mode, both J1 and J3 are forward biased. So J2 is reverse biased. There is a small current flows from anode to cathode. That is the forward leakage current. Okay. In the forward, so when the forward voltage increases, the SCR will be turned on. Uh, breakover voltage means the highest voltage that can be sustained by the SCR to withstand. That is known as breakover voltage. When the voltage increases above breakover voltage, the SCR turns on. When the voltage increases above breakover voltage, the SCR turns on even if the gate drive is not applied. Okay, but the SCR is not damaged if the voltage VAK, anode cathode voltage, is greater than VBO, breakover voltage. So what will happen if the um, if the voltage increases above breakover voltage, the SCR will be turned on, but it will not get damaged. It will not get damaged only rather than it is turned on. That's it. Forward conduction mode. These are known as turn on methods of SCR. The SCR will be turned on when VAK is greater than VBO. You just remember like this. VAK is greater than VBO. That is anode cathode voltage is greater than breakover voltage. The SCR will be turned on. Then next one, when gate drive is applied. Now only we have seen that gate cathode drive is applied, then SCR will be turned on. Then when dV by dt exceeds the permissible value, that is rate of change of voltage with respect to time exceeds, happens rapidly or frequently, that may be helpful to turn on the SCR. Then when gate cathode junction is exposed to light, okay, at that time also SCR will be turned on because this is because of the photons present in the light. Okay, the first one is when VAK anode cathode voltage is greater than breakover voltage, SCR will be turned on. For that, the connections are made as shown in the figure. This is gate. Okay, this is anode. This side plus this is cathode. Okay, load is also connected. It is connected with the positive terminal of the voltage source. Okay, so slowly we need to increase the voltage. If the anode cathode voltage is greater than breakover voltage, then SCR will be turned on. Then next one is when gate drive is applied. For that, connections are made as shown in the figure. That gate drive is applied. Okay, here SCR is here. Gate is connected to the positive terminal of the voltage source. Okay, anode is connected to the load. Load in terms connected with the positive positive terminal of the voltage source. Okay, so when we apply gate drive, gate cathode drive, the SCR will be turned on. It will go to the forward conduction mode. This is known as gate triggering of SCR. This is the most convenient method. So we are using this method. Okay, this method also we are using this method is also used by many people, many technicians. So next one, dV by dt. When what will happen when dV by dt, that is rate of change of voltage with time, exceeds permissible value, then even if the gate drive is not applied, no problem, the SCR will be turned on, because the forward leakage current. Now in such state, now what will happen, with respect to what will happen, no, just I'll show you the connections. We'll make the connection like this. Okay, so gate cathode drive is not applied, that's okay. But here in J1, J2, one capacitor is formed, and between this J3 junction, P and N, again one capacitor is formed. Okay, so because of that, uh, the leakage current, because of that small current will flow. This will adds to the forward leakage current. So SCR will be turned on even if the BAK is less than VBO. The reason is capacitor's stored charge adds with the forward leakage current. Okay. Next one, when a gate cathode junction is exposed to light, already I told that it is because of the photons present in the light, the SCR will be turned on. Okay, then we'll see what is latching current and what is holding current. Latching current means is the minimum forward current that flows through the SCR to keep it in forward conduction mode on state at the time of triggering. On state at the time of triggering. If the forward current is less than latching current, SCR does not turn on. Holding current, it is the minimum forward current that flows through the SCR to keep it in forward conduction mode. That is the minimum current that flows through the SCR to keep it in the forward conduction mode. When forward current reduces below the holding current, then SCR will be turned off. Now we'll see the two transistor model of SCR. Okay, SCR, we are connecting two transistor. Okay, here this one Q1 and Q2. Sorry, here I have mentioned T1 and T2. I'll show you in the next page. Yes, see, Q1 and Q2 are two transistor. Q1 is PNP transistor. Q2 is NPN transistor. This is anode. This is gate. Gate drive also will be applied here. This is cathode. Okay. The current flows and the arrow marks indicate the current flow. Okay. By using Kirchhoff law, anode current, how we can write anode current? Anode current is equal to IC1, that is here, IC1 and IC2. IC1 plus IC2. IC1, IC1 is nothing but alpha 1 IE1. IC1, this one, no, this current. It's nothing but the current comes from here, no, that is again coming this side. So IC alpha 1 and IE1, like that we can write, plus CBO1. ICBO1 means reverse saturation current. Okay, then IC2 can be written as alpha 2 IE2 plus ICBO2. Okay, here alpha 1 alpha 2 are nothing but these are the current gains of the transistor. Okay, then ICB ICBO1 and ICBO2 are nothing but saturation current. This is due to the migration of the minority carriers from neutral to depletion region. It can be written as IA is equal to alpha 1 IE1 plus ICBO1 plus alpha 2 IE2 plus ICBO2. Okay. We know IE1 is equal to IE1, that emitter current is nothing but IA. Okay. And IE2 here, this emitter current IE2, emitter current of the second transistor, is nothing but IK. So instead of IE1, IE2, we are writing IA and IK here. Okay, this is just you mark this equation because later on we need to substitute the value in this equation. Now by applying the KCL law, cathode current be written as cathode current is equal to IB2 plus IC2. That is base current plus cathode current. Okay, sorry, base current plus collector current. IB2. IB2 is collector current plus IG. IG is nothing but gate drive. IK is equal to IG plus IA plus IC2. IA is equal to IC1 plus IC2. That is anode current is nothing but addition of collector current, collector 1 and collector 2. IK, cathode current is equal to IA plus IG. IA means anode current. Anode current plus IG means gate drive. By substituting this value in the previous equation, I told you to remember, no, mark it as 1. In that we need to substitute this value. We get IA is equal to alpha 1 IA plus ICBO1 plus alpha 2 IG plus IA plus ICBO2. Okay, here just alpha, the terms which are having alpha, no, that we need to bring it together. Okay, this side alpha and IA. So here we have brought it that alpha IA terms here. Then this one is alpha 2 Ig plus ICB0, or sorry, CBO1 and ICBO2, that's saturation current. If we add this saturation current ICBO1 plus ICBO2, then it will, we can mark it as total current, total saturation current can be marked as ICBO. Okay, that's what I have written here, ICBO. Okay, here IA minus IA is the common no in these two terms. So we are taking it outside. IA, open the bracket, alpha 1 plus alpha 2 is equal to alpha 2 Ig plus ICBO1 plus ICBO2. By simplifying this, we can get the answer. Anode current is equal to alpha 2 Ig plus ICBO divided by 1 minus within the bracket alpha 1 plus alpha 2. That's it. Okay, so we finished this one. So if you like this video, you please subscribe. If you have any doubt, you can write it in the review. Okay, we'll see in the next class. Thank you. Okay, these are nothing but again the applications of SCR. They are used in high frequency and low power inverters, high frequency SMPS and high frequency inverters and choppers, and low power AC and DC drives. Okay, that's it. Thank you.